This is the most powerful e-bike I've ever built. It uses a compact motor mount combined with a custom belt drive system to deliver insane amounts of torque. With a setup, you can get anywhere incredibly fast, and it's just amazing how much power the system can produce while staying so compact. The interesting part is that almost the entire drivetrain can be built at home using a simple tools and a 3D printer. This is actually the 4th iteration of this motor. The previous design used a drone motor combined with 2 reduction stages to get down to extremely high RPM. Overall, this system worked, but it had one major weakness. Because the gears were FDM 3D printed, they were not precise enough and started to flex under higher loads. This caused the belt to skip, and when that happened, the entire motor would just lose power. In this new version, I want to get completely rid of this issue, so let's start designing. To solve this problem, I went back to Onshape and redesigned the entire motor mount. The new version uses only 4 main parts, which makes it a lot simpler than the previous design. The main structural part attaches directly to the bike's water bottle mounting holes and holds the entire system in place. Then there are 2 plates that clamp the motor itself and also include a simple belt tensioning system with a bearing. The final part is a frame clamp that adds extra rigidity and prevents the whole mount from twisting under load. And just like on the previous version, I'm using the HTDM 5M belt to transfer the power from the motor to the rear wheel pulley. The rear wheel pulley is actually made out of 2 separate parts. The first part clamps directly onto the brake disc, while the second part is screwed onto it. This makes the design modular because I can change the reduction ratio by replacing only the outer pulley section. The previous design used a 90-tooth pulley, while this version is going to use a 150-tooth pulley. This is because I need to achieve a 10-to-1 reduction with only one stage. For this version, I'm going to be using a FlipSky 7070 110 kV motor. And compared to the tiny drone motor I was using earlier, this thing is absolutely massive. For an e-bike, this is exactly what I want, because I care more about torque than high RPM. According to FlipSky, this motor can actually produce 9.5 Nm of peak torque. With a planned 10-to-1 reduction, this gives us a 95 Nm of theoretical torque at the wheel, which is already a pretty ridiculous amount for such a compact system. The motor also has built-in Hall sensors, which allows the VESC to know the exact rotor position. This improves low speed control and makes acceleration much smoother. I also redesigned the VESC mount, and instead of integrating directly inside the motor like before, I created a separate enclosure above the motor. This makes the whole system easier to assemble, improves the accessibility, and keeps the motor and electronics separated. With the design finished, it was time to start printing. For most parts, I just use PLA. And considering that this mount is going to hold a motor that's capable of several kilowatts, it's probably not the best material. But I already had it, and I decided to see how far I could push it. The motor mount was printed with a 25% gyro infill and 4 walls to maximize rigidity. For parts like this, choosing the right print settings is actually really important. The goal is to find the best balance between strength and material usage, because you simply don't want to turn everything into a single block of plastic. From this graph, we can see that it's more efficient to increase the walls for rigidity than increasing the infill percentage. However, this only works up to a certain point. If you want to print a completely solid part, it is actually better to use 100% infill than maximum amount of walls. And while the printer is doing its thing, let me tell you about my Patreon. If you enjoy projects like these and want to support me in building bigger and more ambitious machines, Patreon is the best way to do that. There I share behind the scenes updates, early access to YouTube videos, extra details about my builds, and even files for projects like these. It really helps me spend more time on these projects and improve the quality of the videos. So to everyone supporting me there, thank you so much. And I think that my part is just about done, so let's get back to the build. I started the assembly with a rear pulley. I replaced the old pulley with the new 150-tooth version and mounted the whole assembly directly onto the brake disc using M3 screws. Next came the motor mount. Since I designed everything around this frame, the installation went pretty smoothly. After mounting the base, I attached the motor and connected the 2 mounting plates using the TPU parts. One of the biggest improvements in this new version is the steel pulley. This should completely eliminate the belt skipping problem from the previous design. It was made by FlipSky specially for this motor, and it uses 15 teeth, combined with a 150-tooth rear pulley that gives us a final reduction of 10-to-1. Another very important part is the belt tensioner. For this, I made a simple sliding mechanism that allows me to adjust the tension precisely. It uses an 8mm threaded rod with 2 bearings at the end. And then the belt was routed from the rear wheel directly to the motor pulley. And honestly, this new system was looking really clean. But it was still missing one key component, and that is the battery. What made my last version really convenient was using a drill battery as the main power source. It made the whole system extremely compact, but it also was something that was holding the bike back. So if I want this new version to actually make use of the bigger motor, I need a better battery. So that generally left me with two options. Number one was to buy a ready-to-use battery, or number two, choose the way harder way and do everything on my own. Yeah, I obviously chose the hard way. For this battery, I'm going to be using 21700 Lion cells. The 21700 basically describes their dimensions. It is 21mm in diameter and 70mm long. Another important specification is capacity. This is usually measured in milliamp hours, or mAh for short, so like a 4500 milliamp cell could theoretically provide 4.5 amps for about 1 hour. And because it is a battery pack, we need to combine them together. And there are actually two ways to do this. You have parallel connections and series connections. Connecting the cells in series increases the voltage while keeping the capacity the same. So 2 cells in series gives us a 2S pack with a nominal voltage of 7.2 volts. Connecting the cells in parallel works a little bit different. The voltage stays the same, but capacity and current capability increase. So 2 4000 mAh cells in parallel gives us a 2P pack with a 9000 mAh of capacity. And by combining both methods together, we can create a configuration like 4S3P. The 4S gives us 14.4 volts, while the 3P gives us 13,500 mAh. But for an e-bike, the capacity isn't the only thing that matters. We also need enough discharge current. You can have a huge battery, but if it can provide enough current, the motor will still not reach its full potential. For my pack, I decided to use Samsung 45T cells, which can provide up to 35 amps of continuous current per cell. Because parallel can share the current, a 3P configuration would theoretically provide 105 amps. So for my battery, I decided on a 10S 3P configuration. That means 30 cells in total, giving us a nominal voltage of 36 volts, a capacity of 13,500 mAh, and a theoretical continuous discharge current capability of around 105 amps. Capacity can be also displayed in watt hours. Unlike milliamps, this takes the battery voltage into account and tells us how many total energy the pack can store. My old battery was around 216 watt hours, while this new one is around 486 watt hours. That is a 125% increase in energy capacity, while the available discharge current is roughly 250% higher. This should finally remove the battery as the main limitation, and let me see what the motor can actually do. Now I just have to build it. I started by creating a layout so I could exactly see how everything is going to be connected. For this, I used some custom 3D printer brackets which work surprisingly well. I also find this website really useful because it shows you all the connections and makes it much easier to check that everything is wired correctly. In my case, I needed to connect all the parallel groups together and then connect those groups in series. And that should leave me with 1 positive and 1 negative terminals at the end. Hopefully. For connecting the cells, we use nickel strips, and this is actually pretty interesting because nickel has only about a 24% of the conductivity of copper. So why the hell aren't we using copper then? Well, because nickel is so much easier to weld. We can't simply solder the cells together because solder is a lot of heat, and cells don't like heat. Instead, we use something called a spot welder. It places 2 probes under a nickel strip and sends a short pulse of current through it, creating a weld between the strip and the cells. This creates a really strong connection without heating up the entire cell. But remember when I said that nickel is so much less conductive than copper? Well, as it turns out, it is a big problem when your battery can theoretically output over 100 amps. Since the current is split between these 3 parallel paths, each path can carry around 35 amps. So to make sure that the nickel strips don't overheat, we need to choose an appropriate thickness and width for the current that they are going to carry. At first I didn't really care, I just bought something that seemed good, and I just connected everything how it should be. But then I kinda just got scared and decided to put a second layer on there. And that should definitely help it carry more amps because I'm not interested in exploding this battery. Speaking of exploding batteries, one of the most important parts of one is a BMS, or battery management system. It monitors the individual cells groups and protects the battery from things like overcharging, over-discharging, and excessive current. It's absolutely massive, but considering the current this battery can output, I would rather have too much BMS than too little. So it basically makes sure that nothing explodes, which is really nice when your battery looks like this. I then isolated the whole pack in Kapton tape, which basically is a high temperature tape that is a really good electrical insulator. After that came the fish paper and the BMS was glued onto the pack. The next big step was soldering all the balancing leads. If you're not soldering it directly onto the cells, it's pretty much fine, you just have to be quick. Each parallel group has its own balancing lead, which allows the BMS to monitor the voltage of every group. This makes sure that none of them are too high or too low compared to the others. You really have to take your time on this because let me tell you, this is definitely not something you want to screw up. After that, I just had to connect the positive and negative terminals to the nickel strips and spot weld them onto the bike. I also added an XT90 anti-spark connector and isolated the whole thing with some Depron padding. With the battery finally finished, I was really excited to mount everything onto the bike, so that's exactly what I did. I also made this TPU pad that attaches to the bike using straps and some screws directly onto the motor mount. The battery just sits on top of it, and for now I temporarily secured it with fiberglass tape. It's definitely not pretty, but it works. After that, it was time to wire everything up, and I installed a new Vesk mount which actually looked really nice. Unfortunately, it turned out to be horrible. The problem was these little magnets I used to hold it in place. They were supposed to make sure that the enclosure stays closed, but instead it kept falling off. So yeah, that's probably the first thing I'm going to change. The wiring also looked pretty messy, so please excuse that for now. But after a lot of work, it was finally ready for a test drive. It ended up working so much better than I expected. This bike is seriously powerful. It can get me uphill at around 25 km per hour without any pedaling, which is honestly just crazy. And for an overall weight of around 5 kg, the whole system is still surprisingly lightweight for how much power it adds to the bike. I'm also really happy that we got completely rid of the belt skipping problem on the motor pulley. It can still occasionally happen at the rear wheel when the belt is too loose, but the original problem is finally gone. The only problem is that the 3D printed structure is still not rigid enough to handle the full power of the motor. The maximum power I can currently run is around 1500 watts, which is already twice as much than the previous version, but this motor should be capable of around 3000 watts. So even though the drivetrain works, it still has a lot of power that I can't use yet. The fastest I ever gone on this bike is around 50 km an hour, and the range has also improved a lot. The Vesk tool is currently estimating around 50 km on full charge, which is pretty crazy. This bike works really well, but I still have one problem with it. I'm still not completely happy with the bike. The drivetrain works, the battery works, the bike is already ridiculously powerful, but visually and structurally, it's still far from finished. The Vesk mount doesn't work properly, there are wires everywhere, and the motor still flexes under high loads. And the whole bike could definitely look a lot cleaner. So this isn't actually the final version. In the next video, I'm going to fix the remaining structural issues, redesign the Vesk mount, do all the cable management, and finally turn this thing into what I originally wanted it to be. A properly finished, powerful e-bike. And this time, I also want to push the motor closer to its full potential, and properly test how much power, range, and performance this thing can actually deliver. So there is still a lot more to do. I want to thank you guys for all the support. It's honestly crazy to see how many of you are interested in this project, and I'm really excited to see where we can take it next. My name is Adam Hayek, I want to thank you so much for watching, and I will catch you in the next video. Bye!